We are now recording, and I'm going to hand things over to Russ. There we go.
All right. Well, welcome everybody. Glad you could join us for the webinar today on understanding color infrared. And as Leslie said, my name is Russ Congleton. I'm a professor of remote sensing and GIS here in the Department of Natural Resources at the University of New Hampshire. Also happen to be the director of what's called New Hampshire View, which is part of a nationwide consortium called America View, which promotes the use of remote sensing and other geospatial information in individual states. And so this is actually the fourth webinar that we've done on remote sensing, and in addition to them being at the VCGI page that Leslie showed you, they're also on the New Hampshire View website if you want to look for them there as well, or find out other things about New Hampshire View. You can do that also, or you can email me anytime with the email address on this page. So I want to jump in because we're going to share time with a bunch of people today, so it's going to be fun. So I did already do a basics of remote sensing webinar back in the fall, and there's a lot of things on there that might help you if you get a little lost in what I'm talking about today, a little more detail. But what I wanted to do is review a little bit and make sure we're all on the same page, and then get into what color infrared's all about, or what infrared energy is all about. So again, it all starts with electromagnetic spectrum, and I think we're all familiar with this. Probably in kindergarten you got to take a prism and divide the white light coming in through the window of your classroom into the various colors, and we realize, as we see here, that the visible portion of the spectrum is a very, very small portion of what we can actually sense in. And so actually fairly early on in history, over 100 years ago now, there was films invented. First, films were black and white films, and then eventually color film, and then actually set things up so that we could sense in some other wavelengths beyond or below what our eyes could see. So we do have ultraviolet film, and we do have what we call photographic infrared, or near infrared film, and you can see those basically in this diagram. But then the real power of remote sensing that's occurred since we've been in the digital age in the last 30 or so years is that we've been able to design sensors that record beyond those wavelengths. And so you can see, passive microwave here, and active radar, and thermal, which is heat, and X-rays, which we're all familiar with, and unfortunately I've had way too often because I tend to break things. But so anyway, that's sort of the whole idea of the electromagnetic spectrum. And what we're going to look at today is specifically what we see in the visible, and then adding on that that short piece that goes a little further up from the visible, called the near infrared portion of the spectrum. And the way that we tend to think about this and look at it from a scientific standpoint is something called a spectral pattern. And what a spectral pattern does is it looks at the response of a particular object across the different wavelengths. And so this is a pretty straightforward spectral pattern. You can see the top line there is an oak tree, and the middle line is pine, and then the kind of blue line that almost goes straight across is simply concrete. And if you look on the wavelengths there, you can see that from 0.4 to 0.5 microns is the blue portion of the electromagnetic spectrum, and then from 0.5 to 0.6 is green, and from 0.6 up to 0.7 is the red portion of the spectrum, and that's what we're used to seeing in. And so if you looked at that, you see this little bump right there, right here, okay, and that's because these are trees, right? So pine tree and an oak tree, and we see them as green, and so they have a peak in the green, and actually the vegetation absorbs the blue and red light, which it uses for photosynthesis, which is basically how vegetation feeds itself. Okay, but then you see further out here into the infrared portions of the spectrum, and this gets really, really interesting once you start to think about what this can do. And actually, this was discovered back in World War II. And what was realized is that vegetation that's healthy gives off very, very, very strong near-infrared reflectance. And so you can see right here these peaks going up this big curve, this is called the red edge, actually. And it turns out to be a measure of vegetation health. So healthy vegetation gives off high near-infrared reflectance, and non-healthy vegetation does not, okay? And so you think about that, okay, you want to hide your tanks, or you want to hide your tent, or, you know, whatever you're trying to hide. Well, you would just cut down a bunch of branches and put the branches of the trees over the top of the object, and if you took a picture of it in color, there would be no difference. You would just look like there's a tree there, and it would hide whatever was going on. And so people said, okay, if we look in the infrared portion of the spectrum, if you cut the branch off a tree, well, that's about as unhealthy as the branch can get. It's very, very stressed, and it actually drops very quickly in its near-infrared reflectance. And as a result, it actually changes color. And so in the near-infrared portion of the spectrum, if we can sense in that, then that would give us an advantage. We'll just look at all the places where the vegetation looks unhealthy, and we'll see in a minute that actually what it does is it changes from a magenta or a bluish red color to this kind of pukey yellow color. So we just bomb all those places, and we would know where people are hiding stuff. And so early on with film, this was called camouflage film, and we know it today as color infrared photography or color infrared film. And then obviously when we got into the digital world, that same thing was extended. And so lots of powerful uses of this for insect infestations or fire damage or pollution, or almost anything you can think of related to vegetation health is important to be able to use the infrared portion of the spectrum. So that's sort of the where all this came from and a little bit of the history behind it. But in order to understand this a little bit more, you actually have to understand what's called color theory. And the important thing about this is there are two different color wheels that we use here. You can see one is for the subtractive color process and one is for the additive color process. Now, film uses the subtractive color process, and the colors that it uses, the primary colors it uses are yellow, magenta, and cyan. And until recently, most of us hadn't heard of those colors, but if you think about the colors that you put in the ink on your printer, that's yellow, magenta, and cyan, and so that goes right there. The complements of that, the additive primary colors, are red, green, and blue, and we have all heard of red, green, and blue. And so if you're going to use film, you have to understand the subtractive primary colors. If you're going to use a computer monitor, digital data, television screen, those work with the additive colors. And in fact, most people call a computer monitor an RGB monitor, where RGB simply stands for red, green, and blue. And depending on what you're putting together, this allows you to understand, if you understand color theory, it allows you to understand what you're seeing with those particular combination of wavelengths. Our eyes only see in the visible portion of the spectrum, and so we've got to fake it out or substitute into those colors so that we can see in other wavelengths. And the way that we do that is we're limited in that there's only three primary colors, so there can only be 3 layers of film, or there can only be 3 portions of our computer monitor, in that case red, green, and blue, in the sense of film, yellow, magenta, and cyan. And so what we do is we substitute things out. So if you were going to look at color film, we would sense in the green, the blue, the green, and the red. Okay, and that totally makes sense, and we would use the film to do that, and we would make things look like normal color photographs. And I'll show in a minute or two a couple of normal color photographs. But if we want to see in the near-infrared portion of the spectrum, then what we have to do is get rid of one of the colors that we're seeing in and add the color infrared or the near-infrared light. And so typically what's done in color infrared film is we get rid of the blue light and we just sense in the green, red, and near-infrared light. And when we do that, we need to be able to understand this color theory, these different charts here, in order to understand why things that we're looking at look the colors that they do. Okay? And so that becomes really, really important. if we were going to look on the computer monitor, same basic thing. We need to understand the color theory so that we can put these things together, because we're limited to seeing in 3 wavelengths simultaneously. Computer could care less about that. If we're going to do digital processing of the data, we could have hundreds of wavelengths, but if we want to visibly see them, if we want to see them on film, we've got yellow, magenta, and cyan, those 3 subtractive primary colors. If we want to see it on our computer monitor, we've got blue, green, and red, the 3 additive primary colors, so we're limited to that. Okay, so here's an example. You can see here's a normal color photograph of an area that's kind of a wetland area, and you can see some trees on there, and then you can see the water on there, and you can see the bare areas and all of that, okay? And so healthy vegetation shows up magenta on color infrared film. It's a combination of blue and red light, because what it's doing is actually, we've gotten rid of all the blue light. It's not letting any blue light in, and the green light is actually being reflected as blue or shown as blue on the film, okay? And then the green light, the red light is being absorbed for photosynthesis, and then the near infrared light is being shined through the red, okay? And so red plus blue forms magenta. If you go back to the thing here, red plus blue forms magenta, okay? And so again, a little bit about the color theory and the why or how this kind of works. The neat thing about this, again, is that you can see very, very clearly that if there was stressed vegetation here, if there was something going on, we would be able to see that with the trees. We would be able to visually detect that. They call it pre-visual stress detection. It's the ability to see this in the color infrared or in the near infrared portion of the spectrum long before our eyes could see it, even if we were standing next to the tree. So if there was insect infestation here, or some kind of a pollution situation, or too much watering, or not enough fertilizer, or whatever circumstance was going on, you would be able to see this on the near infrared portions of the spectrum, which is why I think people these days are very, very interested in not only just having the color imagery, but the color infrared imagery as well. So the 4 wavelengths, the blue, the green, the red, and the near infrared. But you can only look at 3 of them at a time. You can't look at all 4 of them simultaneously, because there's only the 3 primary colors. Also, water absorbs near infrared light, so the water comes out really, really, really black, as you can see on the color infrared photograph. So that will help you out as well for delineating edges. That's really important. One issue that could confuse you a little bit, and you may see some examples of this later on, is shadowing. There's very little shadow penetration in the infrared because there's very little scattering, because the wavelength of light is so long, and as a result, shadows and water can be confused, because shadows come out very, very dark and the water comes out very, very dark. So depending on the height of the trees, that can cause you some issues. Okay, here's another example. I know this is a little fuzzy, but it's the same kind of thing. You can see that the healthy vegetation, they say it's red or pink, but really the right word is magenta. And then the trees that are infested in this particular case are starting to be this kind of bluish green, or I don't know, I call it kind of a pukey yellow type of color. Okay, so here it is digitally. So I showed it to you on film, and with film, again, it uses the subtractive primary colors, but you don't want to get too worried about that. It's just how it's got kind of gets combined together. And so this is just a Landsat image, so this is digital data, and it's showing all 7 Landsat bands. So you can see that up at the top of the diagram here, right in here. Okay, this is band 1 of the Landsat data. So band 1 is blue. Okay, and then this is basically gray tones, so it's a black and white image. Anything that's really, really bright or white on this image is highly reflective in the blue portion of the electromagnetic spectrum, and anything that's dark is absorbing the blue light, okay? And then you look, the next one is band 2, which is the green portion of the spectrum, okay? Same thing holds. Anything that's really bright is reflecting green, anything that's dark is absorbing green. And then the next one is the red portion of the spectrum, okay? And then we get into the near infrared. So band 4 there is the near infrared portion of the spectrum. And then you can see we get into the middle infrared, which starts to get into a combination of reflected light and some heat. But let's just concentrate on the first 4 bands today, because that's kind of where most digital imagery that we would get these days, NAPE imagery and most digital camera imagery, takes these 4 bands. And if you look, we can put only 3 wavelengths together simultaneously. And the way we do that with digital data is we use a computer monitor, which is an RGB monitor, okay, red, green, and blue. So what am I doing? So look at this first image, which we call these composite images, because there's 3 bands put together, okay? And I put 3 bands, band 3, band 2, and band 1. So I've shined band 3 through the red portion of the computer monitor, and I've shined band 2 through the green portion of the computer monitor, and I've shined band 1 through the blue portion, okay? So remember that band 3 was what? Red. Band 2 was what? Green. And band 3 was what? Blue. So I've taken the red, green, and blue and shined it through the red, green, and blue portions of the monitor. So I get what I would expect to get, a natural color composite or a natural color image, or what our eyes would see, okay? So totally what I would expect to have happen. Okay, so that's what we're used to, get our RGB 321 natural color composite. Everybody understands that because it looks like what our eyes see. Okay, but we want to be able to look at the near-infrared light. Okay, so just like I had previously explained, we're still limited. We only have 3 wavelengths we can do. So we're going to get rid of the blue here. Okay, get rid of the blue, and we're just going to use the green, the red, and the near-infrared. Okay, and look how I do it. Same thing. RGB, right? So I'm going to take band 4 and shine it through the red. I'm going to take band 3 and shine it through the green, and I'm going to take band 2 and shine it through the blue. Okay, now that makes a weird thing, because why? Well, because band 4 is not red, it's near infrared. So I'm taking anything that's near infrared, high reflective and near infrared, and shining it through the red portion of the monitor. Okay, and then the red, band 3, I'm shining through the green portion of the monitor, and band 2, which is green, I'm shining through the blue portion of the monitor. Okay, so now look what happens. I get this strange looking image, which I have to understand some of that color theory that we just talked about in order to understand what's going on. Something that's magenta, like this vegetation here, this kind of reddish blue stuff, is red and blue. Why is it red and blue? Well, because it's highly reflective in the red portion of, in the near-infrared portion of the spectrum, okay, and it's reflective in the green, okay. So that's giving me red light and blue light. Red and blue light together forms magenta. Okay. What's also really interesting about this is if you look in this field here, okay, in the color composite, this field is very uniform and looks like, I don't really have much information about what's going on in this field. But if I look in this field right here, the same field, now with the near-infrared composite or the color infrared composite, I see circles that are really, really bright magenta. That means those areas are very, very healthy. Something really good is going on there. But the other areas aren't, okay? And that means that there's some stress or something that's happening there that's not uniform. I'm not getting a uniform growth of vegetation throughout that field, even though when I look in the natural color composite, it looks like I am. Okay, so this is really the significance and the importance of understanding what the color infrared does for us. The ability to sense in the near-infrared portion of the spectrum, especially regarding vegetation, is incredibly useful. And so when we got to the digital world, it was the first wavelength that we've added in. When we got to a lot of the high-resolution satellite imagery that we work with these days, and especially the digital camera data that we're talking about, it was the first wavelength that was added in. And so that's what Leslie and Faye will talk to you about, showing you what's going on with that. So here's another example. Here's, again, a true color composite or a natural color composite around Chattanooga, Tennessee. Again, this is Landsat data, so not that great a resolution, 25-meter data. But again, band 3 is the red, shine through the red portion of the monitor. Band 2 is green, shine through the green portion of the monitor. And band 1 is blue, shine through the blue portion of the monitor. And so, this looks like if you were flying in an airplane and looking down, this is how you'd expect it to look. the color infrared or the false color composite or the color infrared composite. Lots of terminology for basically the same thing. Okay, again, we're limited to using only 3 wavelengths, and so instead of using blue, green, and red, now we've switched and we're using green, red, and near infrared. I'm shining the near infrared through the red portion of the monitor. I'm shining the red light through the green portion of the monitor, and I'm shining the band 2, which is the green band, through the blue portion of the monitor. And again, I get all this nice vegetation, and brightness here is the difference between conifers and hardwoods, and then you could look for places where stress is going on, and then I get this nice black river that shows up, and then the urban areas come out particularly bright and almost white in color. And so this is something that you get used to seeing very quickly, and this is what this whole webinar is about, you understanding what's going on there. So one more slide to kind of demonstrate that again. This one shows a little bit issue of resolution. So on the left-hand side is a panchromatic image, and if you look at that, you probably recognize the Pentagon building at the bottom there, and the 2 yellow arrows are pointing to 2 different fields that are there, right by the parking lots and everything by the Pentagon. And you can see that you look at those 2 fields and they look, you can't really tell kind of what's going on. There's lots of resolution, there's lots of detail here. It's nice and crisp, but it's just black and white. It's just panchromatic. Our eyes only can detect about 200 different shades of gray, and so there's really nothing that we can discern from this image as far as the vegetation goes. If you look at the other image, the multispectral image on the right, you can see that it looks fuzzy. You can still discern the Pentagon, but not as nicely because the pixels are bigger, so it's not the same spatial resolution, but it's in color infrared. And because of that, I can easily tell you, with in 1 second flat, that the one field, the field on the left-hand side, is actually healthy and growing, and the field on the right-hand side, there's nothing there. It's just dirt or soil or whatever word you like to use for that. Okay, and that's because the field on the left is magenta. It's this nice, healthy, growing vegetation that's giving off high near-infrared reflectance, and so in the color infrared, it's going to come out magenta. And the field on the right is bluish kind of color, which basically means it's just the soil that's being exposed there. Okay? So again, there's lots of power in being able to see in the color infrared or in the near-infrared portion of the electromagnetic spectrum, and we simply do that by shifting what we're seeing through the 3 primary colors that we're allowed to see, whether we're talking about film, analog film, or we're talking about digital data and a computer monitor. And so that's sort of the introduction of this for today, and I think maybe we have some questions about this now, and then we'll turn it over and you can see what's available from both the University of New Hampshire and from Vermont's GIS centers as far as data is concerned. So thanks for your attention.
Thank you, Russ. The only question that I got so far, I think you answered right after she sent it in, and that was what color would stressed vegetation be, but then you showed the slide that showed kind of green, yellowy. Yeah.
Yeah. It's pretty obvious. So.
Yeah. Especially compared to the magenta, I would think.
Yes.
So
yes.
If people have other questions, they can go ahead and send them in. I'm going to see if we can hand things over to Faye if she's ready. And Faye, are you ready for me to hand things over to you?
Yep, I'll set.
Okay. But if I get some questions, and I'll go ahead and pose those to Russ. Oh, wait a minute. Another, whoops. Where did that question go? Need to expand my thing. Here we go. So here's a question, Russ. What kind of pre-processing does the data require? For example, atmospheric effects.
Sure. So to see the vegetation health, it really doesn't need any pre-processing. If you were going to do some kind of comparison from one day to another, you'd want to normalize the data, you'd want to take out atmospheric effects so that you could do a more direct comparison. But so it really depends what you're trying to do with the data. But if you're just going up there and taking, you can actually go in a little airplane yourself and fly over an area. And in the old days we used to get color infrared film all the time and do that. You can still get color infrared film, but you could certainly get a camera that somebody who knows what they're doing can jury rig a little bit for you to get color infrared out of that. And so even some of these imagery that I think Faye and Leslie are going to be talking about early on, they were collecting for states. They were collecting just the visible, just the blue, green, and red data, but now most of them are collecting blue, green, red, and near infrared. And
yep.
So yeah, you don't really need to do much processing.
And then maybe a couple more. Is there a way to numerically determine healthy vegetation versus unhealthy? The color is nice to be able to visualize, but to be able to quantify, can you take the IR band and select values, X through X, and say that that's healthy forest, for example?
Sure, you'd want to tie that to the ground, but there are some ratios that can help you with that. There's something called NDVI, the Normalized Difference Vegetation Index, where you would, basically it's a ratio between the near-infrared light and the red light. So since plants are absorbing red light for photosynthesis and they're reflecting near-infrared light if they're very, very healthy, if you take the red plus the near-infrared and then divide that by the red minus the near-infrared, you get a really nice ratio. And what you'd want to do is then go find some places where the vegetation is stressed and not stressed and sort of tie those intervals to the ground. But you could actually do a lot of it without even going to the ground. You just may miss a little bit of the edge here or there. But yeah, absolutely could do that.
And then one last question: does near-infrared imagery, is it able to detect subsurface materials? And the example he gives is something like detecting tile drainage in an agricultural field.
Yeah, so near-infrared light, so there's different wavelengths of infrared light, and what we've been talking about is photographic or near-infrared, which is reflected light. As you get further up into the spectrum, you actually get into what's called the middle infrared or the shortwave infrared, and then eventually into the thermal infrared. And I think if you wanted to detect those kinds of things where you're getting changes in the soil because of things that are underneath the soil, which probably are more affecting temperature, you would want to use a thermal infrared wavelength and not so much what we've been talking about with the photographic or near infrared wavelengths. Okay.
And I'm going to save the next couple of questions just so that we can move on to Faye, but we will come back to them at the end. So Faye, go right ahead and introduce yourself and tell us about New Hampshire imagery.
Okay, can you see my monitor?
I can. Your voice is very quiet if there's any way to turn that up.
Okay.
Great.
I'll try, and let me know if I'm not speaking up enough. So thank you, Leslie, and thank you, Russ. As usual, I learned a lot from listening to you. What I was asked to do is discuss a little bit about what's available for infrared imagery for New Hampshire from the Granite Clearinghouse, and I have worked on the Granite Clearinghouse basically since its beginning in the mid-'80s, so I'm happy to share what data we have with those of you on the webinar. What I've done is just put together a table that lists at least the relatively current imagery we have, or specifically color infrared imagery that we have for all or part of New Hampshire. So there's a fair amount of information here, but I think what's going to be probably of most interest to the listeners is the collection date, which is listed in the left-hand column. So our most recent data as of today was from last summer, and if you move over to the right, one column, you'll see that it's regional. It actually covers only coastal New Hampshire, which specifically is really the coastline and maybe 15 miles inland. That particular image data set is 1-foot resolution, and it's 4-band imagery, so it has the RGB bands as well as the near-infrared band that Russ was talking about. And it's available as geotiffs to people that would like to access it. Moving down, and I won't go through all of these, just point out maybe some highlights. Moving down, we have from 2010 and 11, we have statewide imagery, The intent was to collect it all in 2010, but there were some weather issues up north, so part of the northern part of the state was actually collected in 2011. And it was collected during the spring, so it's leaf-off imagery. It was really done by New Hampshire DOT was the primary funder, and their interest is always in leaf-off imagery. So you'll see that most of the statewide collections that are funded by state entities are typically leaf-off. That is also 1-foot resolution 4-band imagery. And then we go through, we have some 6-inch imagery that was collected in the spring of 2010, and it's available for scattered areas in the state. I can actually show you where that's available. So you get a sense it's not in a contiguous area, but as I said, it's distributed across the state. So that's 6-inch, but also 4-band imagery. And then we have a couple of other regional collections that were from 2005 and 2006. What's maybe worth noting about those 2005 and 2006 collections is that they're not 4-band images. They're simply the CIR band only, so it's a single band image. And because of that, those two particular data sets are available both as GeoTIFF and as compressed SID format files. So in addition to those, and those that I've mentioned have all largely been funded by state sources, or at least sources within the state. We also have NAEP imagery that includes the CIR band from 2012 and 2011. And those of you that may be familiar with NAEP, or National Agricultural Imagery Program data, will recognize that it's collected in the summer because it's collected to support agricultural kinds of applications. That data is 1-meter resolution 4-band imagery, and unlike the other tiles that we distribute, is available in quarter quads rather than a standard 5,000 foot by 5,000 foot tile. So I won't go through the file sizes. I think if anyone is interested in getting this data, what's probably most important to you is how you actually access it. And there's two specific ways, or primary ways, to get it. First of all, Granite publishes web mapping services, or WMSs, for all of the images that were on the prior slide. You can see on the URL here, listed at the top of the slide, how to get to the listing of the WMS URLs. And really, if you just go to the main Granite page, which is www.granite.unh.edu, you can hopefully easily find where this list is. So I've just extracted a subset of it, but what I wanted to point out is that we provide you with a URL to access each of these CIR images on that page. And then for those of you that really want the data yourself, you don't want to access it via a web mapping service, we can certainly provide it to you. Some of these data sets are fairly large, as was represented on the first slide I showed. But we're happy to provide it to you if you provide us with an external drive, a thumb drive or some kind of external drive, obviously of sufficient capacity to host the imagery. We used to request that people send us new drives. We're not so particular about that now, but it's certainly our preference. So those are really the two ways we provide access to the imagery. I would just wrap up by saying that our plans for the future are, first of all, to acquire the 2014 NAEP imagery, which we just ordered yesterday. So we expect it'll be here in a week or two, and then it'll probably take us a week or two to prepare it and publish the web mapping service and have it online and available for people that want to access it. But so I would say within the next month we should have that available to anyone who's interested. And secondly, we are working with the New Hampshire Department of Transportation on acquiring statewide 1-foot resolution 4-band imagery for this spring. So hopefully by next fall we'll have another statewide data set that will be similar in content and resolution as this prior statewide collection. That's all I have. I'm happy to answer any questions that people may have.
Okay, thank you, Faye. Let me just see if we've gotten any new questions. Oh, actually, since you mentioned the leaf-off imagery, I want to answer these other two questions here that I think you and I can answer between us. One of them asks the question about leaf off. This person comments that he's seen leaf off 4-band imagery, but does collecting imagery when the leaves are off defeat the purpose of obtaining the IR band? And as we just saw with the imagery available in New Hampshire, there is both leaf on and leaf off available. My understanding is that leaf off 4-band or near infrared is still very useful because, and this is going to answer the other question that was mentioned, which is about using it for finding water bodies and wetlands. It is obviously still very useful for identifying water bodies and wetlands, whether the leaves are on or not when it's taken. And it also can be very helpful in terms of identifying coniferous as opposed to deciduous trees. So I don't know if there's, if Faye, if you want to comment any more on that, but that seemed like
well, I might just add that if we have projects that require doing vegetation mapping specifically, then we typically look for a combination of both leaf on and leaf off and try to create composites that sort of express the best of both worlds.
Right. Okay, great. All right, I'm going to switch things over to me now, and there I am. Okay, so what I'm going to do to show you similar information to what Faye just showed you about what's available in New Hampshire is I'm actually going to just show you on our website. If you go to the Data and Imagery section of our website and then click on Imagery over on the left, you'll see a little list of downloadable data right here, and you'll see that indeed color infrared imagery is one of the options. And so we can just take a quick look at this table. Maybe I can make this a little bit bigger just so everybody can see it. And you can see that we have the statewide Vermont orthos, which in the past were black and white. Starting in 2011, we began collecting them as color IR, so they are the 4-band imagery. We don't quite have the whole state done because we do a chunk of the state each year, but if you look at the things that say Vermont Ortho here, you'll see that the 2011 imagery is Rutland and Windsor counties approximately. 2012 is Addison, Orange, and part of Washington. 2013 is the northwest part of the state, Chittenden County and Franklin, Grand Isle counties, a little bit of Lamoille as well, and then the data that has just been released that was collected last year is the northeastern part of Vermont. So everything except for the southern chunk of the state, we do have half-meter 4-band imagery, so that would include the infrared. In addition to that, we do have some higher resolution imagery for Chittenden County that was collected in 2013. The eastern portion of the county was collected at 20 centimeter resolution, and the remainder of the county, the western part, sort of 2/3, was collected at 15 centimeters, and that also is 4-band. You can also see that we have NAPE imagery. We have 2012, we have 2011, we also have 2008, and again, that's not actually 4-band, that's, or no, yes it is. Color IR. Now I can't remember actually whether this is 4-band or 3-band. I'm not sure why it's CIR. I think it might. No, I think it's color. So we do have it from 2008, 2011, 2012, and as similar to Faye's situation, we recently got the 2014 NAPE imagery, and we are actually in the process of dealing with it and turning it into state plane and also making it into a service. So that's the quick way to figure out what we have available for download, and I'll just point out that we do offer these for download in 2 different ways. If you were to simply click on the icon under the word download, you'd see a rather cryptic list of tiles, but fear not this cryptic list, because if you go to the top, anytime you're faced with this at our website, go right to the top of the list and you'll see that there's a PDF index map. And if we just zoom in on that map a little bit, we'd eventually be able to see the names of the tiles. We'd pick out the ones that we're interested in, go back. Oops, Actually, I went back too many steps. Go back to find the tiles that we're interested in and just click on them to download them. So this is if you just want a fairly small area or maybe a few different tiles. You might go about it this way. The other option that's available for much of our imagery now is the custom download. And if that was what you're interested in doing, you would just zoom in a whole bunch until you start to actually see the imagery. Now because this is 4-band, so it's not just IR, it is all 4 bands, what you're going to see eventually when we zoom in quite a bit is it's just going to look like natural color imagery. There we go. But be assured that if it says color, oh, this actually is just color. Sorry. Anyway, if you see color IR, it will be, the 4th band will be in there as well. So the next step is just to define your area of interest, and then you would pick your file type and go ahead and download it once you had done that. All right, so there's 2 ways to download the downloadable data. We also do have web map services. And you can see that sort of the top of the list here is the imagery services. And if we scroll down just a little bit, we see best of color infrared imagery. We also see color infrared Vermont orthos. So the distinction there is best of color infrared imagery. Whenever you see best of in any of our services, it just means it's kind of a pile of all different imagery of all different sources and at various different resolution levels, and it's called best of because it is designed so that when you use it in your mapping software, it will show you the most appropriate imagery for that particular zoom level. So as you zoom in, you may end up seeing higher resolution imagery, and as you zoom back out, you'll see the lower resolution. So the best of color infrared would include the NAPE imagery for when you're zoomed out a little bit more, and then some of the Vermont ortho color infrared as you zoom in a bit more. But if you just want color infrared, you can also get, right now it's only the 2011-2012 because we haven't created the services yet for the 2013-14 imagery. And then you also can get just the NAPE color infrared down at the bottom of the list here. So I think that's all I wanted to point. Oh, no, there was one other thing, and I'm glad that Faye pointed this out for her imagery. You can also get the imagery on an external drive, although we do things a little bit differently here in that we don't do it on kind of a custom basis, and we don't take your drive and put the data on it. We just have 4 data products available. One is all available imagery, which means you will get whatever infrared and color infrared imagery we have on that drive along with everything else. And then we also have the uncompressed and compressed statewide NAPE and the Vermont orthos, and both of those would include any 4-band imagery that's available as well. And the cost for those is $170 for the all imagery, and then $125 each for these for the NAPE imagery or the Vermont ortho imagery. So that is what we have available, and I think that I'm done talking. I'm going to open up I'm going to unmute Russ and Faye, and if anybody has any other questions about either accessing Vermont or New Hampshire data or about using it, or questions for Russ, I'd be happy to take those in and pass them along.
So Leslie, I just wanted to say about the question about leaf off and color infrared. Certainly if you were interested in water, as you mentioned, or things like vernal pools, or seeing anything underneath the trees, that's what, there's still lots of uses, as both you and Faye said, of the color infrared even for leaf off. Although if you're looking for vegetation health, you're not going to learn anything about it with leaf off, but there's other reasons, like you guys said. So I concur completely with what you guys commented on there.
Great, thank you. I'm sorry I didn't unmute you for that.
Oh, that's okay. It's probably better that way.
Okay. Does VCGI offer free LiDAR data, or is it buy only? Oh, that's an unrelated question, but I would be happy to answer that. very briefly. So yes, what you can get from us, if we go to our data data warehouse here. So what you can download from us for free are the derived products that are created from the LiDAR data. So what you'll see in this search results table are a whole bunch of different things that are created from our LiDAR data. Digital elevation model, aspect, digital surface model, hillshade, NDSM, and slope. So these are all available for download. The original point cloud or last data, if it's available to us, is only available on that drive. And the primary reason for that is size and pipe size and just dealing with big chunks of data and how to make them available to people is something we're still trying to figure out the best way to do that. Actually, Faye, do you guys distribute LiDAR data? Oh, maybe Faye's not there anymore.
No, I'm here. I just forgot to unmute myself.
That's okay.
We do have a site. It's lidar.unh.edu through which we distribute the LiDAR products. So we handle it a little differently than our other image products, but definitely distribute it.
Neat. And you distribute the point clouds and the last data as well? Yep. Okay, cool. Well, we're going to be trying to figure out what we should do about our LiDAR data soon, so I'll point this out to my colleagues.
Okay.
Thank you. Any other infrared questions out there, or have we answered all questions? I think we've done too good a job.
Nothing wrong with that.
No, I know. All right. I know as soon as I say okay and I'm going to let everybody go, that's when a question's going to come in. But thank you very much, Russ, and thank you very much, Faye. And, yep, there we go. Does near-infrared imagery... Oh, no, that's the same question. Sorry. No, I think someone sent in the same question they already sent in before, which is about whether it can be used to isolate water bodies and wetlands. And the answer to that is yes, it can. Because it shows
if anybody has other questions, they can certainly email me. My email address that was on the first slide there. So
yeah. So thank you, everybody, and I will be posting the recorded webinar at our YouTube page, and as Russ mentioned, it will also be on the New Hampshire View page soon after that, I think. And if you have any questions, you can always pass them to me, and I'll be happy to pass them along to anyone if you didn't catch any of the contact information. So thank you again, Russ and Faye, and have a great day.
Thanks, you too, Leslie.
Thanks.
Right.